Good evening and welcome to this edition of your Daily News. I'm Jackie Hayway. To tonight's top story, researchers at the University of Queensland have cracked a possible new viable treatment for the ongoing crisis of malaria. The conquest of this disease has seemed too steep of an uphill battle for centuries, but what many don't realise is that it has been driven out of entire continents in the past, done so by extensive campaigning, education, and by no coincidence the invention of a new anti-malarial agent. Luckily for us, mosquitoes are just an itch that we can scratch, but according to the World Health Organization, for almost half the world's population, malaria is a serious risk and can have fatal consequences for the sick, the young and the elderly. University of Queensland's Diane Keough and Guddat published their work on the malaria parasite in 2013. Now, I'm fortunate enough to have Diane here with me today to discuss their work. Thank you for joining me here today, Diane. Well, the pleasure is all mine. Firstly, Diane, how does a researcher come about coming up with a new possible anti-malarial therapy? Jackie, I can tell you that it all starts with an idea. To pick one part of the parasite to target without adversely affecting the host cell. And believe me, that is the most difficult and most crucial step to overcome. So this target you mentioned, it is parasite specific then? Not quite. We actually chose a target that is found in both human and malaria parasite cells, shutting down an enzyme known as CHEM2052. It is essential for the recycling of your DNA, the subunits of which are constantly being broken down and remodeled for countless other tasks that a cell must do in order to survive. Without this enzyme, you would not be able to recycle the metabolized products of DNA, and you would have to make these from scratch every time. The cells are quite capable of doing this, though it is much less energy efficient. However, the malaria parasite does not have this option. It needs CHEM2052 functioning in order to survive. So basically, once you stop the enzyme, you stop malaria. So how were you able to inhibit the action of this enzyme, and how effective was it? We took known inhibitors of enzymes from other diseases, including HIV and HPV, and modified them by attaching a carbon, 2 hydrogens and a fluorine to a specific point on the inhibitory molecule, which basically formed a DNA imposter. The enzyme CHEM2052 binds to these imposters, thinking that they're the real deal, and it gets stuck, disabling its function of recycling old nucleotides. I've brought my model with me here today, just to show you exactly what we did. In grey and blue up here we have guanine, one of the 4 bases of DNA, and this long black and red mess is the inhibitory part of the compound. So now if I take this off and put my carbon, fluorine and 2 hydrogens on, we now have the CHEM2052 specific inhibitor. So now with the salvage pathway inhibited, the human cell has to make the nucleotides from scratch, while the malaria parasite has no choice but to die. As for effectiveness of the molecule, we found that by adding the fluorine group we had up to 1,000 times greater affinity to CHEM2052, which means tighter binding and overall greater sabotage of the enzyme and its recycling process. Well, thank you very much for coming to talk about your work, and best of luck to you in the future. Thank you, Jackie. Thank you for joining us, and good night, Australia.